And today, Professor CASSANDRAS will review for us the illustrious history of perturbation analysis and his own early contributions to that work until today. So please help me to welcome Professor Christos CASSANDRAS.
Thank you, and thanks to David for organizing this great event. And I would like to echo him in what he said about the gold standard of academic success, which is definitely not the bibliometrics, but really the way in which organically one earns the respect of one's colleagues. And in this respect, Professor Ho is just way off the charts, period. So I chose to give a talk which is not very technical in homage of Professor Ho, because my interactions with him started when the term discrete event dynamic system did not exist. The term perturbation analysis for DEDS did not exist, and he got me into that area. That was not what I was planning to study when I started out. And I'm glad that I chose not to make this a technical talk, because having Sophia here and some of the non-technical members of Professor Ho's family, this is your last chance to understand some things. After that, it's all downhill for you guys. So this is not a super technical talk. However, the danger I always see with these talks that talk about history and story is that they tend to dwell on the past. So I promised myself when I designed this talk that I was not going to fall in this trap, and at least 20% of the talk was going to be about the future and the present. So you can hold me to my promise. I will do that. So here's what I want to do. I want to tell you how, more or less in 1979, a real problem gave birth to an academic discipline, a whole research field, and a toolbox for practical problem solution. So going back to the question that I think you asked, this is a perfect example, and David alluded to that, of how we saw, Professor Ho saw, a problem from the real world, and he didn't know much about it. We didn't know much about it, but we got into it. We learned just enough to make contributions. In the 2 decades that followed, I will quickly take you through the chronology of the field of perturbation analysis. And in 2002, personally, I thought that by 1999 it was over. Okay, I mean, the field had reached its plateau, that's it. And then shortly thereafter, there was a rebirth, really, of a special type of perturbation analysis that we call IPA, infinitesimal perturbation analysis. And this was helped largely by the emergence of hybrid systems. So nowadays, pretty much everything's a hybrid system, and IPA is an amazing tool that you can use, and it works like a charm, where it had really encountered some intellectual blocks by the late 1990s. So the last part of my presentation will be to summarize for you what we now call the Ipa Calculus, and how it meshes very well with another new direction in control theory, for those of you that are into systems and control, that we call the event-driven approach, which in many ways has reinvented control theory from the 60s, but hopefully it has gone above and beyond that, especially with the fact that data-driven methods are now in fashion. And perturbation analysis was actually a very natural data-driven method. Okay, so here goes. More or less, in 1978, Fiat is the company that you were trying to think of, had a problem, and this problem was, what is the best way to distribute buffer capacity in a manufacturing transfer line? So if you look here, it looks more or less like a line, and there are large objects, chassis of cars, that have to be positioned accordingly. And it's a reasonable question, if I have so much space in this particular building or room, how do I allocate my space in a judicious manner? So if I were to abstract this a little bit with pretty pictures, there's a line where parts are coming in, and they get processed in these purple blocks until they become useful products to go out. These are serial operations, and in between you have some space. And the question is, how do I allocate the space? Equally, not equally? So here's an example. If you're given this many buffer slots, then maybe the way you allocate them is 2 here, and 3 there, and 1 there. Why might you want to do that as opposed to balancing them? Well, perhaps because this is a pretty fast operation, so there's really no need to queue up too much here. As soon as things come out, they just need to go through, whereas this is slow, so you need to compensate for this slowness relative to the previous one by buffering a little bit. That might be one way to do it. But how do you systematize that? How do you really do it? And the complexity of solving a problem like that, the sort of the brute force way, for k buffers to n stages, just to give you an example, for what I would consider a rather small system, contains about 120,000 allocations. So a brute force trial and error method, which would be what most people would like to do, if you were to do it under these assumptions of about a week of observing how, trying different combinations would work to get statistically meaningful results, would require this many years. Clearly, we don't want to do that. So let's say that you can prune this 120,000 big space down to about 1,000 promising allocations. That would cut down to about 19 years. And if you use simulation, which is the way that, right now, of course, you all think, of course, we use simulation. But remember, this was 1978. So back then, simulation was not your natural first inclination. And when it was, I would assume that it would take about 3 minutes per trial. So this would cut down the whole task to about a year in terms of working days. Clearly, slow and painful. Not the way to go. Now, first of all, why is this an important problem beyond, let's say, buffer allocation? Pretty much every manufacturing system that runs in a serial way, and even if it's not serial, has to deal with this problem of processing from left to right a certain number of products. And there are these competing metrics, throughput, which you would like to maximize, and delay, which you would like to minimize. So an increase in lambda, the incoming rate of raw material, increases the throughput, which is good. But at the same time, the average delay increases, which is bad. And no matter what assumptions you want to make about the lambda and the different rates or the modes in which this operate, there's always a curve that trades off between throughput and delay that looks more or less like this. It might look sharper, it might look smoother. It doesn't matter. It almost always looks like this. And the important thing is this sort of transition from almost flat to this very, very sharp rise, which means that what you really want to do is find the sweet spot and try to keep the system operation over there, where the delay is low before it shoots up when you're approaching your capacity of the throughput. So that's why this is an important problem. So the two key observations that took people a couple of years to realize is, first of all, this is definitely a dynamic system, but it does not look like a system that you can model with differential equations. Actually, I tried. That was my first task. And you can do it, but it's so contrived and unnatural that you kind of have a feeling in your gut, this is not the right way to go about solving the problem. So we needed a new modeling framework, which eventually led to discrete event dynamic systems. The other thing that you realized is that you really don't need this brute force trial and error method. There are clever ways in which you can do thought experiments. What if we did this? What would have happened then? Okay? And this is what led to perturbation analysis. So these were the two guiding principles that eventually created both fields, discrete event system and a subfield of that, which I would call PA, perturbation analysis. So let me take you through kind of a cartoonish kind of depiction of how the concept of perturbation analysis works. And the important thing here is to realize that, yes, this system of these three stations, workstations A, B, and C, undergo some dynamics. Yes, they're not x dot equals ax plus bu dynamics, but they are dynamics nonetheless. So let's see also how the interaction between components, because that's what system dynamics is all about, understanding how components of the system interact with each other. How do they occur here? So this is a part that comes and, of course, goes through A, and we call this an event called arrival 1. And there may be an arrival 2 and an arrival 3 and so on. Okay, this is boring so far until we now move one of these parts from A to B. That's departure 1, so another one takes its place. And then maybe the next event that happens, and this is where I don't know which event is going to occur next. But let's say this is the next one. It moves to C, and then maybe another one comes. Notice that here we see the first time that something undesirable is happening, idling. Because I have parts here, but I don't have anybody to feed to this machine B, so this is idling, so that's not good. But the interesting thing happens a little bit later. We get another departure from A to B, and now we get another departure from B to C. That's okay, but now let's say that we get one more part there, and the next thing that happens is a departure from B to C, and it can't go anywhere because we have no space. So this is what we call blocking. So this is where you realize that having only one buffer slot here is not good in this particular case, and you'd like to do something about it. Well, more events may occur, and so on and so forth. And this is where you start asking yourself, what if I had this virtual buffer there? Can I say something about what might have happened? And the answer is yes. If this virtual block had been added, then I would have been able to take the part that is blocked here and doing nothing meaningful but just sitting in a machine and put it in this extra space here. Moreover, I know exactly at what time this would have happened, so I can record that. And this is observable. So that's the first observation. Then we wait a little bit longer, a few more events occur from the left, until finally this event occurs, which frees up the buffer slot. The blocking ends. And this is also a time that I can record. So in a nutshell, if I was, I don't even call it smart, but just aware enough to record the time when the observed blocking started, think about what would have happened if I had had this part there, and then wait until the blocking ends. This difference tells me what I would have gained if I had had this extra block buffer over there. So this is really the idea of perturbation analysis. This is something you can do in your head. And of course, there's more, but this is the starting point. Okay, so to make a long story short now, learning by trial and error involves, for any system really, but in our particular case we're interested in discrete event type systems, involves a process in which you set various design options, policies, and parameters to observe performance measures. And the conventional trial and error analysis, what we call brute force, involves repeatedly changing parameters or operating policies, scheduling policies, whatever you have, testing different conditions, and answering a lot of what-if questions. And in particular, if you have n what-if questions, you realize that you need n plus 1 trials, the nominal situation and then all of the what-if questions, which is slow and painful. So here's what perturbation analysis does for you. It creates this extra box in here, which interacts with the system in both ways, actually typically more in this way. You just make observations. And in optimization, you need the other way. And then, in addition to providing the system with this yellow information so you can get this yellow output, you provided a bunch of blue information, which are what-if questions. And I'm not talking about 10 or 20 or 30. I'm talking about thousands at a time. So that when you get in one trial the output here, you get answers to your n what-if questions over here essentially for free. Answers to multiple what-if questions automatically provided from a single trial. This is the overcoming of the slow and painful learning process that is unnecessary. And of course, this sounds like magic. Or so we were told, and Professor Ho alluded to that in the early 80s by people who were not very happy to hear that, hey, we had a good idea that may have, invaded their field a little bit. In fact, there was a controversy, not just for perturbation analysis, but really in discrete event systems. And I'd like to share with you this that was shared with me by Professor Wanham, another one of the main contributors to the development of discrete event systems. And I shared this with, in several plenary talks that I've given with a broader audience. So I'm sure that some of the people in the audience were people that made comments, such as the one I'm about to show you, as reviewers for work on discrete event systems, which in Wanham's case was really on supervisory control as opposed to perturbation analysis. So here goes. Here were the reviews. A reviewer who rejected the submission from Automatica. Automata have no place in control engineering. Mathematical systems theory. FSM, finite state machines, and regular languages are nothing new at best and trivial at worst. And this work, actually, they accepted it, but why did they accept this paper? If it's optimal control, we'll take it. That was the reason. So I want to share with you what Murray Wanham's conclusion was, and I like this. crossing cultural divides can be a chilly business. I think he has a British sort of background, so this is a British way of saying this sucks. So this is what happened, and of course we had similar controversies, and Sheeran was involved in those in the operations research community, but you see it goes broader than that. All right, end of parenthesis. So going back to the magician, how did this happen? Is it black magic or not? Let me share with you a very, very simple, intuitive way that you can see why perturbation analysis works, period. Okay? And the reason why it works is this, in this particular example, which relates to buffer allocation. Suppose you have this little model where there's a machine, a buffer, parts arrive, parts depart, and suppose that you started out with 2 buffers, the green trajectory. So this is the content of this little system for 2 buffers, okay? And this is how it evolves in terms of what's the content, in terms of time. And this is how I can think in my head how it would have evolved if 2 was replaced by 1. So the ceiling of the buffer, instead of being at 2, has been pushed down to 1. Okay. So the first thing you realize that until you actually see this event, which is perfectly observable, in other words, you see an arrival when the buffer content is 1 and it just hits 2, everything's the same. There's nothing really to measure. So if I define delta x to be the difference in the state between the 2 systems, the delta is 0. Here's where the first interesting thing happens, and the interesting thing is that the blue system accepts it, accepts the part, the second does not. So delta x becomes -1. Very obvious thing, I can record it. Now, after that, everything stays at -1. It's very easy to see. You can see the second part, which departed over here, would have departed over here. I lose the third part because there are only 3 parts that could have been processed because of my lower ceiling over here, but that's okay, because by the time I see the service time of the 4th part, which is over here, I can paste it over here. My delta x remains -1, and finally, the green system becomes empty, and of course, the blue system is also empty. And from this point on, resetting things delta to delta x equals to 0, all I have to do is wait for the next arrival and repeat the cycle. So everything is very easy. All you got to do is wait for this critical event, set a delta x equals -1, wait for this other critical event, reset your delta x, and go on. That's it. Now, of course, I'm oversimplifying it. Of course, it's not that easy when conditions and the parameters that you're perturbing are different, but you get the idea. There is no magic. Okay, so to understand why this is important from a more mathematical point of view now, consider brute force derivative estimation. So now I'm going into derivatives and gradients. The brute force approach, in terms of measuring the derivative of a particular performance criterion with respect to a parameter vector of interest, theta, let's say that is a scalar for the time being, would be to run the system under theta, run it under delta theta, estimate, that's why I have these hats there, because I'm assuming that the system is not deterministic in general, and then my estimate of the derivative is given by this ratio. 3 problems. The first is that in a real system, this is very intrusive. I have to go in there and do something, tweak a particular system that may not be easy, certainly not in a manufacturing system, and not in many other systems that you are not allowed to just go and tweak things. And so that's not desirable. Secondly, there's the computational cost. Yes, if it's only 1 parameter, so this is a scalar, I only need 2 trials. But if there are n parameters, I need n plus 1 trials. And again, I'm thinking of n being in the thousands and tens of thousands, so this is not efficient. And from a mathematical standpoint, perhaps the most crucial problem is the inherent accuracy of this estimate. Because if delta theta is large, then you have a poor derivative approximation if that function as a function of theta is nonlinear. If you pick a delta theta which is very small, then chances are this difference is almost 0, this is almost 0, and you have 0 divided by 0, you have numerical instabilities. So you can't win. So this is why perturbation analysis comes with its magical box, and in the case of gradients, we call this infinitesimal perturbation analysis, and delivers this estimate without any need to specify a delta theta. Don't have to guess. It just happens. It's just a particular algorithm that gives you this estimate. And of course, the question is how good is the estimate and so on, which we then try to address. This is just a a sample bibliography of some of the key papers over the years. I've included some papers, since we're talking about discrete event systems developing at roughly the same time in the early 80s as perturbation analysis, and selected books through the years that have documented all of this work, as you can see. Okay, so infinitesimal perturbation analysis, which is a special class of perturbation analysis, basically focuses on just real valued parameters, theta, and asks the question, what if this theta is very, very, very small, so that I can eventually estimate a derivative as opposed to a finite difference. I won't get into the details, as I promised, I'm not going to get technical, but I will show you the universal algorithm that answers this question for any event-driven system, any discrete event system. So, initialization. You look at all of your events, okay? So if an event, say alpha, is feasible at your initial state, then you initialize this derivative estimator, where v is the lifetime, the clock value for that particular event. If you simulate, then this is something that you know because you generated it. If you don't simulate and you observe the real world, you wait until this event occurs, so you know how much it took. For every other event that has nothing to do with the parameter theta, you set this particular perturbation evaluator, if you will, to 0. And then you wait for events. So let's say an event beta occurs. Well, then two things can happen. It's possible that any other event alpha might be equal to beta, is activated again with a new lifetime. For example, if you have a queuing system, you have an arrival process, then with every new arrival, you reactivate that arrival, and that's all that happens. So then you compute this quantity, and there are ways in which we know how to compute this. This is the sensitivity, the derivative of the lifetime of that particular event with respect to theta. And then this is the way that you couple one event to another. And this is it. That's all you need to do. Of course, there are many questions. What is the quality of these estimators? This is actually where it got controversial, because admittedly, in the early years, we were not really very careful about guaranteeing unbiasedness, consistency, and so on. The qualities that you always expect of your estimators. But it turns out that the answer is yes, these are good estimators for a large class of discrete event systems that includes GG1 queuing systems and a large class of queuing networks. And the only limitation at this point is that, as I said, for this algorithm to work, you need a parameter theta which is real valued. So I can't really put under this umbrella the integer valued buffer capacitors that we were talking about before. All right, so that's the limitations. So this brings us to the question of unbiasedness, and this is a question which has to do really with whether you can interchange a derivative and an expectation operator, because this is really what you're observing as your cost metric. You want to take the expectation of it and the derivative, but this is really what IPA gives you. So the question is this IPA estimator unbiased? Is it possible to interchange the derivative and the estimator? And of course, there's a whole theory that developed on that, and maybe Sharon will have more to say about that. So now I'm going to take you very, very quickly through a chronology of what happened through the years. From the early days, in 1979, the first, to my knowledge, PhD student that was involved with perturbation analysis published a paper with Professor Hall, and that was really the first paper that talked about perturbation analysis. Then we published a paper which was, as far as I know, the very first one that introduced the term discrete event dynamic system. And then the floodgates opened. I'm putting here the names of various students, some of whom, of course, are here, and various papers emerged. This is the time of the controversy, which introduced extra players that were not part of the Harvard group at the time in order to create a peaceful coexistence. We're moving into the late 80s, and we have smooth perturbation analysis that makes its appearance, which generalizes IPA. The first book that really appeared was due to the work of Glasserman, who put a lot of the missing theoretical pieces together when it comes to the issue of unbiasedness. Then more people came along. You may recognize a lot of his names. We started working on optimization methods driven by perturbation analysis techniques. I have a different color of this because this is where we started asking questions about what if the parameters are not real? Okay, they're integer valued. Can we develop a parallel perturbation analysis theory for that? And we were able to move on. And again, more and more different types of papers, including some people like Ed Chong and Peter Ramage, who were not part of the Harvard group, and others like Bremot and Vasquez Abad that came on board with different variations of perturbation analysis. And we move into the 90s. Things are beginning to get a little difficult to make advances in the theory because the problems were getting harder and harder and harder and harder. And at this point, some people made real heroic attempts at making final contributions to perturbation analysis until I thought, at least in 1999, that this would be the last word on perturbation analysis. This was a paper which we referred to at the time as the mother of all perturbation analysis. It could answer any perturbation analysis question you wanted at the expense of computational complexity. But a few years later, we realized that it was possible to actually use hybrid system models of difficult, complicated discrete event systems, and we sort of developed a new way of using IPA, infinitesimal perturbation analysis, to do fluid models. It took a number of years before we came up with this paper in which we put it all together, and that gave rise to the Ipa Calculus that I will close my talk with. And I wanted to just flash a bunch of papers here because they show how IPA in the last 10 years is used in all sorts of different areas now, even cancer treatment. We've been able to use IPA because hybrid systems have opened up the floodgates. IPA works with just about every hybrid system in the world. So manufacturing, in multi-agent systems, which has nothing to do with discrete event systems, and also in traffic control. So I'm going to close with just a very, very quick run of what the Ipa calculus is about. Just keep in mind that these primes correspond to derivatives with respect to theta and not time. And I'll skip this. This simply gives you a sense of what stochastic hybrid automata are, which are the most general systems that you could have. And the Ipa calculus consists of three equations, basically. Assuming that your hybrid system moves from one event time to the next during which these dynamics are in force, you have the first equation, which tells you how the derivative of your state with respect to the parameter of interest, okay, jumps potentially from one event to the next, okay, after an event, from one time to the next, based on the dynamics before and after, but you need also to know the event time derivative. Okay? If that's true, if the state is continuous. If the state is not continuous, then you just simply apply an even simpler equation based on a reset condition. The second equation is simply an equation that tells you what happens in between events. In fact, this is nothing else but a linearization of a nonlinear system. So if there's no discrete events, IPA comes down to this equation. The third equation, the final one, has to do with the event time derivative. That depends on what kind of events you have. If the events are exogenous, meaning they do not depend on theta, then the answer is 0. If they are endogenous, the most interesting case, then you need to know the switching function, the function which determines this change. And then you can do some simple calculations which link the event time derivative to the state derivative. And then there is another case for induced events. So these are the three equations that really define IPA. That's it. Of course, I'm omitting the details, but that's all you need. And I'm closing with the three properties that make it useful. Number one, robustness to noise. It really doesn't matter what the noise models you use are, almost always. Not always, but almost always. Number two, decomposability. You can decompose a trajectory in terms of certain events, which makes the calculation easy. And this is perhaps the most useful, scalability. Everything in perturbation analysis is event-driven. Therefore, the computational complexity scales with events, not with a state space. Nowadays, people talk about time-driven versus event-driven control. So this is where the state of the art is in control theory in terms of time-driven methods. And if you replace this stopwatch with a switch, then you move into what we call event-driven systems. And this is the generalization of control theory because I can always define an event to be a clock tick, so I'm getting back to this model, And this is where the world is today. This is a number of relevant publications. And I'm putting this up for those of you who are not perhaps into discrete event systems, perturbation analysis. This is really the new trend in control theory. So in conclusion, we start with a buffer allocation problem which developed the basic PA technique. We moved into continuous parameter optimization, which is the use of IPA. If unbiasedness works, then we can do optimization. If unbiasedness doesn't work, we seek all these other alternative techniques. But sooner or later, we get hit by complexity, which is where we are today. We have overcome complexity to a large extent through the Ipa calculus for hybrid systems. And overall, the perturbation analysis story is really one of complexity management in optimization and control. Thank you.
Thank you very much. One thing I learned from Professor Cassandras when I was a young graduate student is you always give your talk all the way to the end so there's no more time for questions. That way you don't have to question him on anything. So yeah, unfortunately, I think we should move ahead with the next talk, and we'll defer the questions to offline if that's okay. Thank you very much again, Professor Cassandras.